Hi, good morning, everybody. Welcome back from the break. My name is Tyler Jacks. I'm the director of the Koch Institute here at MIT, which is MIT's Cancer Center. And I'm happy to be introducing the Health and Medicine session for today's festivities. Let me open my remarks by congratulating Vladimir Bulovich, the director of MIT.nano, and President Raphael Reif and Provost Marty Schmidt for this very exciting and very important day and very important initiative for MIT. I've been watching and waiting as the MIT.nano project was conceived and designed and constructed, not least because it blocked my favorite path through campus. But here we are today, and it's extremely exciting. And it's actually a very important facility and set of resources for the Koch Institute, the institute that I direct. The Koch Institute is an interesting cancer center. You wouldn't find it anywhere else on a college campus in the United States, probably around the world, because it brings together cancer scientists and cancer-oriented engineers and physicians to think about cancer-related problems and come up with new solutions for the disease and the most challenging problems associated with it. A major focus for us in the Koch Institute is nanotechnology applications, and MIT.nano will be tremendously valuable to my colleagues who pursue these very, very important applications. And I'll just give you a few examples of people in the Koch who will be taking advantage of what MIT.nano has to offer. Angela Belcher is developing new materials at the nanoscale for discovering tiny tumors that are invisible to the surgeon's eye and will allow better surgical outcomes for patients with ovarian cancer and other forms of cancer. Paula Hammond is developing nanoparticles that can deliver combinations of powerful anti-cancer drugs with unprecedented precision. Sangeeta Bhatia is inventing new materials that can serve as biosensors for the earliest stages of cancer and allow the detection of the disease through a test no more complicated than a simple home pregnancy test. And Dan Anderson and Bob Langer are developing new materials, again, at the nanoscale, to deliver whole new classes of medicines, including, for example, recently packaging the components of CRISPR technology into particles to deliver to healthy and to diseased cells. And the Koch is really just one part of a much larger biomedical ecosystem that exists on our campus, which literally touches every corner of the campus. MIT.nano is really at the epicenter of a remarkable collection of biomedically oriented activities at MIT and beyond. It sits next door to the Koch Institute, to the Reagan Institute, to the Broad Institute, the Whitehead Institute, the Pickauer and McGovern Institutes, and the departments of biology and biological engineering, Institute for Molecular Engineering and Science. All of these entities and more are actively engaged in the pursuit of questions related to normal biology, health, and disease. And the technologies that will exist, that now exist in MIT.nano, are incredibly powerful. And the impact goes well beyond the MIT campus. We sit at what is, in fact, the most densely packed set of companies and other activities associated with biomedicine. This is the biotechnology valley in the world. In our immediate area, we have 18 of the top 20 pharmaceutical companies, all of the major medical device companies, 250 biotechnology companies. In Massachusetts, in the last decade, there have been 11 million square feet of lab space built, which brings the total to nearly 30 million square feet of activity. Venture capitalists have invested in 2017 alone more than $3 billion to support biotechnology activities in the state of Massachusetts, to bring scientific ideas to new products to help patients. Juan Enriquez made the point very nicely about how important this little dense area is to MIT and to the world. He described the corner of Vassar Street and Ames Street, the corner near the Stata Center and the Koch building, and I'm quoting now, if I had to pick a single corner anywhere on the planet as the most innovative and productive crossroads in history, that would be a leading candidate. And so it really is remarkable what exists here and how MIT.nano can help advance the activities of all of those entities and individuals. So in this short session that follows, there isn't time to capture all of that excitement, but I promise that the three speakers will demonstrate the creativity and brilliance of MIT faculty who are tackling problems using technologies at the nanoscale to improve our understanding of biology and health, and ultimately to help us control deadly diseases. Shortly, you'll hear from my colleague Katarina Ribik, who's the Hyman Career Development Professor of Biological Engineering, and she'll tell you about where the wild things will be found and how to tame microbes in the nano era. Thomas Schwartz, who's the Boris Magasanik Professor of Biology, will elucidate why the nanoscale is so important in structural biology. And indeed, using cryo-electron microscopy, we've now a new revolution in how to understand the structure of molecules and complexes. And that wouldn't have been possible here at MIT if not for the MIT.nano building. Before we hear from Katarina and Thomas, Dr. Elazar Edelman, who is the director of MIT's Institute for Medical Engineering and Science, will bring our focus to translational medicine and how materials, medicine, and health merge through the synergy of science and technology. I hope you enjoy this session, and now let me welcome Elazar to the podium.
Thank you, Tyler, and thank you, Vlad, for the opportunity to speak today. Are my slides going up? So these are my affiliations. I'll talk a little bit more about them because the one truism, as Tyler alluded to, is academics cannot realize potential without affiliations. Regulatory agencies, other schools, but in particular industry. When we talk about microscopy, when we talk about imaging, we ascribe, perhaps erroneously, the invention of the microscope to Antonin Leeuwenhoek. But what most people don't realize is that he was a material scientist. He was a draper. And he and his family wanted to figure out what made the best drapes. And so he invented a technique for making good lenses. But he was also the antithesis of an academician. He published nothing because he was quite proprietary. And the man who rightfully should be accredited with bringing microscopy into the modern age is Robert Hooke. He was Boyle's assistant for the gas law, Hooke's constants, Hooke's laws. But he also coined the term histology because when he looked at cells, they looked just like this pattern behind me of a honeycomb. And he coined the term histology. But the truth is, neither of them were the first. Ideas of microscopy are inherent in the essence of humankind. In 1850, Austin Leonard unearthed this 3,000-year-old lens. It's a polished rock quartz crystal that was found in the Assyrian palace town of Nimrud, where undoubtedly Assyrian scientists were looking at the sky above and the earth below. If you ask what the essence of humankind is, it is, for me, the legacy of innovation. The triple helix of not being able to exist without examining the world around you, refining and disrupting it, and then doing what no other species does, which is to pass that on to other people, even those that are not immediately present, to each successive generation. And so when I talk about MIT.nano, it's not about a scale. It's about a perception, a paradigm. It's a thought process. And what I'm going to do in the next few minutes is talk to you about that nano thought process that allowed us in our lifetimes to reduce the mortality of the leading cause of death and disease in the United States and across the world, cardiovascular diseases, sixfold. We live in a remarkable time. In our lifetime, your chance of dying if you've had a myocardial infarction, heart attack, the diseases I treat, has dropped sixfold. How many people here know of someone, by applause, who had a heart attack? How many people know someone who's got an endovascular stent, a metal stent? How many of you know that every FDA-approved metal stent went through the MIT Biomedical Engineering Center before it entered clinical practice? That's what I was afraid of. So now I'm going to tell you the story. So just so you know, what we routinely do now is thread catheters into the heart, and in an area of obstruction, the first thing we do is we put a balloon. We inflate a balloon, we push everything aside. We call it angioplasty, but for the materials and mechanical scientists, it's angioelasty. And then, to prevent recoil, we place a metal stent. It's actually quite remarkable. The truth is that even though it's only come into existence in the last 20 years, it was first conceived of in 1912 and then again in 1960, but it wasn't until this man, Julio Palomaz, and Cesar Gianturco actually made it a reality that it came to fore. So one of the questions is, why did it take so darn long? Why did it take until the 1990s for this wonderful technology to come to fore? Now, part of it has to do, to a great degree, with the way we think, but to an even greater degree, to the tools that we had. This is one of the first subjects ever to get a stent. This is a pig. And we put stents in cured heart disease in lots of pigs. The problem is that here you see the stent embedded in the coronary artery. It's really hard to take out. And so early on, the best that we could do was actually put stain on top of the stent, and wherever there was metal, the stain didn't penetrate, and where it did penetrate, we see the beautiful appearance of endothelial cells of the lining of the blood vessel, and where there was injury, we see that those cells are denuded. Early on, we knew this was a problem. This is my colleague Campbell Rogers, and in the 90s, we knew this was a problem. We couldn't quite figure out what it was until brilliant MIT students, and they're the unsung hero of absolutely everything we do, came and explained using finite element analysis and other computational methods, because that's where the balloon that you saw before hits the artery. But the real problem is, couldn't actually figure out what was going on. So Campbell and I went to Morris Karnofsky, the father of vascular biology at Harvard Medical School, and we asked him if there was a way to cut the stents in section. And he said, sure, you need this device. It needs this device, which is called a slammer microtome. And we asked him, well, Professor Karnofsky, where is the slammer microtome? He said, well, every shipyard has one. So every Saturday, Campbell would take our specimens and drive down 95 to Mystic, Connecticut, and we would pay Sam to cut our specimens on the side from my wallet, and we would get the most extraordinary images. Eventually, we worked with Leica to make a microtome that could actually be used for biologic processes. And in fact, one of the side benefits of actually driving to Mystic, Connecticut is it forced us to not only develop insight, but to develop tools. Eventually, what we showed was not only could we highlight the good and the bad, but we could actually change the stents that Julio had introduced. And this stent, this prototypical stent you see here, the stent that Campbell and I helped invent with a company called Advanced Cardiovascular Systems that became Guidant, that is now Abbott, was the first stent to still 1 million stents in the United States. And in every respect, it was superior. But it was superior only because we had the first invented tools and the insight. Within a few years of our publications, the ability of the stent to improve survival for patients who underwent balloon angioplasty, just the balloon alone, rose dramatically. If you have bypass surgery, which is a brutal surgery, you can survive a year with only 10% downside. It takes about 6 months to recover. Balloon angioplasty, you recover instantly, but about 40% have to come back. By the time we introduced stents, we dropped that to 25. So how did we narrow the gap? Well, what we thought was perhaps we ought to give drugs. And so we did a variety of experiments. Mark Lovich was a student. We published data which showed unequivocally that powerful drug like heparin could actually dramatically reduce the amount of tissue growth into the stent. So I walked around or ran around the country telling everyone to give heparin to the patients, and sure enough, patients who got heparin did miserably. Nobody ever shows you their miserable data. I'm showing it to you. The green is what happens when you get heparin. The higher the bar, the worse you do. So being humiliated, I tried to do an experiment where I said, well, you actually didn't do the clinical trial the way we did the animal experiments. And they said, well, go do the animal experiment the way you want us to do it, and then we'll believe you. So here, up is bad. So I gave heparin every other day or every day. That's what your prescriptions have, QOD, QD. We purposely use language to make it confusing, right? And then I said, let's give it the way in which we really want to give it, frequently. So I asked my technician to work with me to give it twice a day, and then I realized by the time we got going, it was 9 o'clock, and by the time we planned for the end of the day, it was 3 o'clock. So I said, we have to do it every day at 6 a.m. and 6 p.m. And she said, good luck. So I recruited the only person that would work with me on this, my son. And for a whole month, he and I went in 6 a.m. to 6 p.m., and lo and behold, we did great. Now, I was Bob Langer's second graduate student, and I was actually injecting animals twice a day like a fool. And my son said, you're Bob Langer's second graduate student. Why are we injecting these animals? Why don't you make a device to give it to him continuously? And I said, good idea. So I had such an impact on my son that today he's a professional comedian. But I did work with Guidant to make the stent that elutes drug. Now, the problem was that when we started with heparin, it did great in the first 3 days. Heparin-coated stents prevent stents from clotting, but they don't prevent stents from going over. And what students did is, using our microtome, they showed that if you cut the sections every 40 microns, which you can only do with this new technology, you can't get any heparin into the artery. Other students came by and they showed that the mathematical models show that if you enter in all the constants, the velocities, et cetera, for heparin, the stuff just pours out. And so what they said was, if you pay attention carefully to fixed laws, that it's not unusual. There's no volume to a stent. It's all surface area, so everything's going to dump out. The only way to do this is to change the diffusivity. And so what we did is we looked up in the pharmacopoeia the drugs that had the lowest solubility and diffusivity. And one of the drugs we chose was paclitaxel, and the other, sirolimus. We did it that way. We chose them because of their physical chemical content, constants. And when we did that, we actually showed that you could increase the amount of drug that went into the artery 30-fold. And then what we did was what you do in the lab. We made a beautifully elegant drug-eluting stent, which looks like cotton candy on a metal wire. But when we put that in, and we used confocal and 2-photon microscopy, which was then in its infancy, we showed that you could see the map of penetration of the drug 200 microns deep into the artery. Had we not had that, it wouldn't have ever advanced what was going on. And so within a short time of publishing the first papers that showed that drug-eluting stents actually almost eliminate entirely the vascular reactivity, for the first time an interventional technique surpassed the surgical technique for the treatment of a critical disease. We went within a very short time, within a 10-year period, from a 40% failure rate to a 6% failure rate for a technology which now is used in about 3 million people across the world. Everything's great, right? Until I took care of this patient. This was a Army veteran who came in with crushing pain. He was having a heart attack. Here's his EKG. It has what we call 2 stones elevations in his electrocardiogram. We put in stents. We put in bifurcation stents, 2 stents, in the proximal portions of his artery. Unfortunately, this gentleman liked his recreational drugs more than the drugs he needed for his stents, and so he left the hospital on the first day against medical advice. And he came back literally a month later to the day, and here's his angiogram. You don't have to be a cardiologist to see that there should be a branch here and a branch here, and the branch here is just gone. And what we sucked out was this clot, which was the cast of his coronary artery. Now, this was happening across the world, and there was mass hysteria. In fact, the FDA issued a warning, pulling the first generation of drug-eluting stents from the shelves. The New York Times published papers saying they caused terrible things to occur. So what did we do? We went whitewater rafting. Took the lab whitewater rafting because MIT students love adventure. And while we were on the whitewater, I said to the guys, we got to solve this problem. We have to go, and I have to present to the panel of the Food and Drug Administration. And so Brinda Balakrishnan said, it's a fluids problem. It's a fluid dynamics problem. It's a flow problem. The reason you get whitewater is because you're disrupting flow. When you put the stent in, you're disrupting flow. So we need to make better stents that do less disruption of flow. And Kumaran Cohen-Develu said, it's not just a flow problem, it's a surface problem. We need to address the surfaces. We need to show that some surface areas are inherently thrombogenic and others are not. And sure enough, what we did, working with the FDA, was to actually explain when stents are thrombogenic and when they're not. Now I'm going to skip ahead for the sake of time and just go through and skip these last 2 slides and get to the end. It has been a remarkable journey. It has been a journey that over the last 50 years, we've reduced mortality of cardiovascular disease 6-fold. By harnessing technologies, we have allowed a technology to emerge which failed over 100 years ago to come to clinical fruition. We did so because we created a conceptual community and took advantage of incredible resources. In 1966, a few years before he died, Lord Florey, who won the Nobel Prize in 1945 for the synthesis of penicillin, came to visit with Morris Karnofsky, who we had worked with. He wanted to study the endothelial cell. And he wrote the following thing in the British Medical Journal. I would expect to see exemplified the dicta that the introduction of a new technique is certain to be followed by new discoveries, and that the pushing of a known technique to greater heights of technical achievement will produce new accretions of knowledge. To me, MIT.nano is not a scale. It's not about millions or billions of square feet or dollars or scales or angstroms or nano. It's a way of thinking. It's the creation of communities like this where the legacy and footprint of humankind is the absolute need to characterize and classify, to refine and disrupt, to conceptualize, and then to communicate for all generations to come. And so, grateful to all of you for listening, to Vlad and MIT leadership for the opportunity to speak, and all of these people at MIT, in our institute, IMES, at CBSET, and at the FDA for allowing me to be a part of this journey. Thank you.
You just heard of Antony van Leeuwenhoek and how he crafted one of the first lenses. And his lens was so powerful that he discovered a mysterious new world. It was populated with funky, tiny wild things, which we now call bacteria or microbes. Many of these bacteria, microbes, are incredibly helpful for humankind, but others are ferocious and together cause more deaths than any war. 100 years ago, we discovered antibiotics. This has been a magic bullet and one of the greatest advances of therapeutic medicine. We had found a way to combat some of the deadliest pathogens. But it is also an arms race. Antibiotics put evolutionary pressure on the microbes and drive them to develop antibiotic resistance. And we now have multiple antibiotic-resistant bacteria, so-called superbugs. These are a growing concern. We need to do better at taming these wild things. So, what's next? What if we could step out of this arms race and instead form an alliance with these problematic pathogens? What if we could tame them, if we could domesticate them? We provide them a safe place to live and food, and in return, these critters agree to protect our health and maybe even equip us with entirely new skills. I'm a biological engineer, and my wonderful research group focuses on unraveling the mysteries of one of the most fascinating materials in biology, mucus. Mucus is the battleground of our interactions with the microbial world and has been taming problematic pathogens for millions of years. Mucus lines all internal surfaces in the body that are not covered by skin. This is more than 2,000 square feet inside of your body. And there, mucus fulfills many different functions that are vital for your health. For example, it helps preserve moisture on your epithelia, such as the eyes, the mouth, and the lungs. And it also protects your stomach from digesting itself. But mucus is also a major ecological niche for microbes. You see, most of the trillions of microbes that grow on and inside of your body grow inside the mucus in your digestive tract. And many of these critters are incredibly important for your health because they help you build vitamins, they help you digest food, and some even protect you from other harmful pathogens. Mucus provides a habitat where these beneficial microbes can thrive and benefit the body, and they have no temptation to leave. They have a safe place to live and food to eat. But in this crowd of beneficial microbes are also problematic pathogens which can cause infections. In fact, it is a wonder that we are alive. Over millions of years, mucus has evolved strategies to control problematic pathogens. And this is important. Mucus does not kill the microbes. Instead, it tames them. And it tames them with the help of mucin molecules. Mucins are the building blocks of the mucus gel. They look like tiny bottle brushes, and they're densely grafted with sugar molecules. And these mucins bind to other protective molecules, such as from the immune system, and to microbes. And this is what helps keep us healthy. You see, the goal of a microbe is to eat and to divide. They do not want to harm us. This is why presenting to them sugar can help. Sugar is food for the bacteria. I'm so excited about mucus because I'm convinced it can help us find new strategies to protect us from infections. My group and others around the world, and here is really the importance of MIT.nano, have begun to build mucins and mucus, and we want to use it to control problematic pathogens inside and outside of the body and stop the growing threat of antibiotic resistance. But we also want to use mucus, we want to leverage it to domesticate microbes that could help humans thrive on the planet. If we learn how to domesticate microbes, we could end the arms race. And these critters could help us adapt to harsh environments and even gain entirely new skills. Here are a few ideas. If we could harness microbes to sustainably build food in our digestive tracts, this could solve starvation. Microbes could also help us become more salt tolerant. If we could drink salt water, this could solve the shortage of drinking water. But microbes could also help us tap new sources of food and, for example, extract minerals and nutrients from substances we don't currently consider as food, such as those found on other planets. This could help us colonize new planets. Now, this may seem very far out, but remember, microbes grow in all sorts of places that we currently consider uninhabitable. And if they grow there, they are harnessing materials from their environment for food, and they can feed us too. 340 years ago, Antony van Leeuwenhoek discovered a mysterious new world of tiny wild things, and we're just learning about the incredible power of these microbes in the ecosystem of our body and mucus. By engineering mucus and mucines, we can domesticate these microbes, creating a new era of opportunities for humankind. And I bet MIT.nano will be at the very forefront of this endeavor. Remember this next time you blow your nose.
Okay, good morning, everyone. My name is Thomas Schwartz. I want to spend the 10 minutes that I have trying to convince you why MIT.nano is so exciting for us biologists and for structural biologists in particular. And so this has to do with why do we care about nanometer scale. So something that you're all familiar with, which is at this point high school knowledge, is this like how a DNA double helix looks like. So you have two strands of complementary bases, and essentially you can then form two types of base pairs, an AT or TA base pair and a CG base pair. And so this is sort of, if we want to understand function, and so we need to know the structure, this seems on the one hand trivial, on the other hand, when you look at the difference between these two base pairs, it's actually pretty subtle. And when you actually see those structures, you need to have a resolution of significant detail so that you can see these minute differences between those two base pairs. And so therefore, we need to look at these molecules in that detail. And that detail is essentially a nanometer scale. It's actually less than a nanometer scale. So nano for us is kind of cold coffee because we care about angstroms. So even one magnitude, order of magnitude lower than nanometers. And so if we have this kind of detail, then we can specifically say, for example, in a DNA molecule, how these bases look like and whether it's a TA or a CG base pair. We can do the same exercise for another major class of biological molecules, which are proteins, the workhorses in a cell. So this is, as an example, what we call a GTPase or a switch molecule. It's the oncogenic RAS protein. And as you can see, it moves between two states, and they are determined by a small molecule that binds to that protein. And this is already a totally simplified cartoon, because if I would show you the 1,500 atoms, you wouldn't understand anything. So we have to sort of simplify this down in this type of cartoon form. And then, okay, so in the oncogenic form, of course, this protein is stuck in the on state, and that then generates proliferation, uncontrolled proliferation of a cell. All right, so how can we visualize this? So how do we get to this angstrom scale? So this has to do, of course, with microscopes and magnification. So if we look at a regular light microscope, can resolve differences of 200 nanometers, and our eye can differentiate a fraction of a millimeter. So in the end of the day, we get a 1,000-fold magnification. If we now, however, want to really look at 2 angstroms, or 0.2 nanometers, so which is 1,000-fold more, we then need a microscope that has a million-fold magnification. And so that's all good and fine. So we need a microscope that uses what we call X-ray energy of this type of wavelength. The only problem with this is that there are no lenses for X-rays, and therefore you cannot build an X-ray microscope. And so what we therefore have done for the last 50 years, we used sort of a substitute for that. It's called X-ray crystallography. So instead of using a microscope, what we do is we crystallize the protein or the biological macromolecule. Therefore, we then arrange millions of copies in a crystalline array and can amplify a signal. If we now take X-rays and illuminate the sample with it, what we get is a diffraction pattern that per se we cannot understand, but we can back calculate from the diffraction pattern what the actual structure looked like, and then we can arrive at these structures. And we need simply this very high energy and very brilliant X-ray light, and for that we go to several synchrotron facilities throughout the country. And so this has been extraordinarily successful. And over the last 50 years, we solved worldwide way more than 100,000 structures of biological macromolecules this way. And so that's all great, and we can do this with, it's not just many structures, these are also very complicated structures. So here is an example from my lab of a really large assembly of about 40,000 atoms in the end that, is all wonderful, and we can see how these proteins interact with each other. But the problem is, this took us about 10 years, and this is not sort of the everything we care about. This is still only a fragment of an even larger assembly that we really care about, which is called the nuclear pore, or the transport channel through which all the material that has to be transported inside and out of the nucleus of every human cell traffics. And so this is then essentially impossible to do with X-ray crystallography. And the problems are, essentially, we need a ton of material, which is expensive to produce and takes a long time. We need to coax everything into crystals, which is an empirical process. Even after 50 years, we don't really understand how this works. And so it may work, or it may not work, and can be very frustrating. And these molecules have to be quite rigid, otherwise they will not crystallize. A flexible molecule does not want to be coaxed into a crystal. So these are limitations. One can, however, build a microscope with very high energy. Then we are talking about an electron microscope. And so you can accelerate electrons to 200 or 300 kiloelectron volts. Then you get a wavelength that is way smaller than what we actually need. And that's wonderful, and we can build lenses, electromagnetic lenses. But the problem is that while doing this and illuminating a biological sample, you essentially destroy it while you look at it. So this is nice for material science, but when you do soft material, like in biology, this is essentially a no-go. So by freezing the sample and by applying all kinds of tricks, people have figured out ways of using a cryo-electron microscope for biological samples. And for many years, these were limited to a very small subset of very large and very specific molecules. And there it was great, but it wasn't really widely applicable. And what happened 5 years ago is that the cameras that are used in these microscopes could be dramatically improved. And instead of using a CCD camera, you can now use a direct electron detector. And so that can directly detect electrons. It has like two major advantages. One is that by doing so, you immediately create a much better signal-to-noise ratio. And we can record not just still images, but we can record movies. And so, for example, this probe, while it's being illuminated, actually moves. And it also gets destroyed. And so we can follow these processes now in a way in this movie. And so we can unblur the pictures, and we can figure out something about the decay. And that's what you can very easily see in those two images, of course, that this one is way sharper than this one is. And the result is that we have an almost order of magnitude improvement in the resolution, and this is extremely exciting. So the advantages are that we now use much less material, and we don't have to put it into a crystal anymore. And we also are not as limited to sort of rigid molecules as we were previously. And so this makes cryo-EM now really a super exciting technology, and in structural biology, essentially the largest sort of dramatic change over in the last 50 years. While everything else was essentially gradual, this is really a quantum leap. So we need these microscopes, but these microscopes are very, very expensive, and they need environment that we can only find in one location on MIT grounds, and that is MIT.nano. And so therefore we were very fortunate when we were looking frantically for a place to put these microscopes 5 years ago, that MIT.nano was just in construction. And I cannot thank Vladimir enough for opening the door for us and allowing us to sort of build this there. And there's also the other people I want to thank is Dennis and Nick, who sort of really made sure that these rooms are built the way they need to be built. This is really a very, very special environment. And so these microscopes are being built. They are on schedule. We will be able to use them by the end of the month or months later. And of course, as I said, these are very expensive tools. And so this did only work with massive support from within MIT and from sponsors like the Beckman Foundation and others that really enabled us to do so. And so therefore, we are very excited about what we will be able to do in the nano building and what we can do in biology, but this goes way beyond sort of just biology. It includes other departments and ideas as well. And with that, I want to thank you for your attention.
Well, so MIT.nano is not the first organization that tries to bring people together. Indeed, MIT has in times past done exceptionally well in recognizing that we are much stronger when we can share ideas across the boundaries. I had an absolute privilege of being a part and leading an organization known as the Microsystems Technology Labs that now is being led by the next speaker I'm about to introduce. MTL is an extraordinary place that has taught us in so many ways how to actually bring together different disciplines and through that be able to enhance everything that we do. Without further ado, I would like to introduce the director of MTL, Professor Jesus Del Alamo, who will tell us about the integrated systems and how the revolution rages on. Thank you.
Yes, good morning. President Rife this morning referred to the raging artificial intelligence revolution and the importance that hardware, computing hardware, is playing in it. And that is precisely the topic that I would like to have some remarks on today. In fact, I'm going to show you an example that comes from the lab of Vivian Z and collaborators at MIT for a very compelling application of artificial intelligence, which is autonomous drones. These are very small drones, as you can see in that picture compared with the coin, that are designed for search and rescue operations in disaster environments, such as, for example, what results out of the earthquake and tsunami last week in Indonesia. This is a very challenging environment where tiny drones have to be able to go in, navigate through a very complex situation, take a mapping of the situation, take important images, get sensor data, and then fly out and then report everything. And of course, all this is done without access to the internet in situations like this. As you can imagine, this is a very challenging application because of the complexity and because the device has to be completely autonomous and there is very little energy to work with. The chip that you can see there, you can see how small it is called the Navion. And the design of that chip, that's where all the smarts are, really has to be done in an extremely careful way to be able to have the energy efficiency that is required. So artificial intelligence is enabled by essentially three things: the algorithms, the data sets, and the computing hardware. Now, the algorithms have been around for quite some time. And what has made this sudden burst of intelligence, of artificial intelligence, is the availability of very large data sets, but also the progress that has happened recently in computing hardware. And that's the topic that I would like to emphasize in this talk. Now, artificial intelligence applications ride on the most advanced silicon technology. And as Ray's data reminded us this morning, this is a revolution in itself that has already been going on for over 50 years. You can see in this chart, for example, the number of transistors that can be integrated together on a microchip, which is now well exceeding 10 billion, and that has been doubling every 2 years. This is truly remarkable. And this, of course, has fueled tremendous progress in computation and in many other areas of human concern, such as health, transportation, communications, energy, etc. And in fact, the progress is all for us to see in a very evident way. A supercomputer 10 years ago, the power of computation of a supercomputer 10 years ago, today you can have it in the palm of your hand, just in your cell phone. Now, MIT, let me see if we can go back. Can I go back one slide? Yes. MIT can be very proud of having significantly contributed to the microelectronics revolution. And I'm going to show you two examples. In the late 80s, Dimitri Antoniadis and Hank Smith fabricated some of the smallest transistors ever made at that time. And so that was a feat in itself that was truly remarkable. But the most important result that came out of that was the realization that in such small dimensions, electrons travel significantly faster than was expected from the conventional drift diffusion theory at the time. In fact, the electrons travel in a ballistic fashion, significantly higher velocity. So the first observation of this phenomena at room temperature, which was done at MIT by this group, really pushed out the limits that were perceived for silicon technology and really opened the horizon to significantly more progress in the future. Now, a few years later, in the lab of Judy Hoyt at MIT, she was investigating very thin strands of silicon nanowires, as they're called, and making transistors by having the electrons travel up and down through these nanowires. And as you can see in this picture, she made truly remarkable small transistors. The diameter of that silicon nanowire in the picture is 8 nanometers. Just to calibrate your length scale, 8 nanometers is much smaller than the smallest virus that is known. It's truly small. And yet she was able to make working transistors like that. But furthermore, she was able to figure out that if you now apply tensile strain to these nanowires, you stretch them, then the electrons travel much faster. And that, again, conceptually, was able to push out the limits of silicon technology into the future and was adopted by all companies in the microelectronics world. So a lot of progress has happened. This has enabled the AI revolution, but looking forward, it's getting harder to continue to push microelectronics into the future. And so this could represent a problem and could become again the bottleneck for progress in AI. And so a compelling application of AI is, for example, autonomous cars. As you can easily see, this is an application where cars can be significantly safer, and there can also be significant enhancements in in fuel efficiency. So this is an application of tremendous interest for humanity. But it also is a very demanding application. So for an autonomous car to be useful, it has to be able to make correct operational decisions faster than a human. And so the number that I have seen quoted is about 100 milliseconds. A car must be able to respond within 100 milliseconds to a given situation. Now it turns out that requires massive computational power. And that can only be accomplished today with electronics that involve chips that have been very carefully designed for that very application. They're called application-specific integrated circuits. And in fact, if you look forward and you try to achieve even greater accuracy in more complex situations, then there is a need to use higher resolution cameras which produce that much more data, which totally overwhelms conventional electronics. So what is to be done here? Well, something that can be done and that is being done is the co-design of the algorithms and the hardware very carefully. The Navion chip that I showed you at the beginning of this talk, made in Vivian C's lab, is a perfect example of co-design of the algorithm and the hardware. Another example is the one that I'm showing you here. This comes from the lab of Song Han, a new professor at MIT, which is working, among other topics, is working here on a system for object detection that could be used also for autonomous cars or for surveillance applications. Now, the system on the left is a fairly conventional system that, as you can see, can handle images at a frame rate of 4 frames per second. The system on the right is a system designed in Song Han's lab, which using new techniques that are called pruning and compression and designing a hardware that is optimized to implement those techniques, is able to achieve a frame rate of 30 frames per second. So with such a higher frame rate, we're much less likely to miss an important scene and therefore able to react much more quickly. This is an example of the power of co-design of algorithms and hardware. But eventually, the underlying technology needs also to make progress. One of the great problems in AI, particularly because of the large amounts of data that are involved, is that the distance between the compute engine, the logic, and the memory, where all the data resides, is actually quite far apart, relatively speaking. And the pipe that connects the two is relatively thin. So the data has to go back and forth from memory to logic, back to memory, at a rate that is limited by this pipe. To really improve this, what we need to do is to bring the logic and the memory together in a much more intimate contact and to open a pipe that really allows the data to transfer back and forth in a very speedy way. Ideally, what we'd like to do is just put the memory right on top of the logic on the very same chip and connect them with very high bandwidth connections. And that's precisely the work that Max Schulacker is investigating at MIT. He's developing a new technology that he calls monolithic 3D integration, three-dimensional integration, in which he brings layers of logic, various transistor technologies, and memory, various types of memory, all on top of each other, connected with very high bandwidth vias, very fine density of very fine vias that connect everything together, achieving, therefore, a very high throughput in the management of information. But the beauty of this is not only that you make things go faster, but is that this new system design also allows you to now come up with new system architectures. And a particularly important one that is raising a lot of interest today in AI is what is known as in-memory computing, in which now this construct allows the memory itself to do some basic operations, such as, for example, matrix multiplication, which is one of the core operations that happens in AI algorithms, without having to go back and forth between the logic and the memory. The operation is done in the memory itself. Now, there is a lot of interest, thinking again, going beyond, into doing processing not in the logic domain, in the digital domain, but in the analog domain. And in this regard, there is the notion of creating networks, as you can see in this picture, of small analog resistors that are programmable and that are non-volatile, and that allow you to create these networks that can do matrix multiplications in a very efficient way from an energy point of view and with very low latency. Now, the thing is, that this is a completely different device. And today, we don't know of any material system, of any device construct that can implement this. So here is where MIT.nano comes in to really allow us to now bring in new material systems that work under new physical principles to design these new devices to enable these kinds of applications. There are colleagues at MIT that are working on this. You see here some pictures from the work of Ji-Hwan Kim, who is investigating the use of dislocation, a very specific crystallographic defect in silicon germanium under certain conditions, down which, or rather up and down which, he can get metallic ions to move in response to the application of a voltage. So in that way, he creates metallic pipes, tiny metallic pipes, that he can control through the application of a voltage and therefore program a resistance and then read the resistance and then reprogram it as necessary. And so he has demonstrated devices with really very promising electrical characteristics. He has also done, as you can see in this picture, a 16 by 16 array, also with very nice characteristics. What's beyond? Well, there is no lack of concepts. In fact, the next whole new wave out there that looks tremendously exciting and promising is quantum computing. I won't say much about it because I don't know much about it, and because there's a panel that is following that the Dean of Science, Michael Sipser, is going to lead in a moment, so I will let it at that. But before I finish, I want to make one final point. As Vladimir suggested, all the research that I have shown you here has taken place, or is taking place, at the Microsystems Technology Laboratories at MIT. This is a lab that is dedicated to advancing microsystems at MIT for all manner of applications. MTL has been privileged for over 30 years to run the nanofabrication facilities at MIT. Now, with the construction of MIT.nano, it makes sense for all our facilities, all our equipment, and all our personnel to transfer to MIT.nano. So I want to use this opportunity to salute our loyal staff, fab staff, which are pictured here, for many years of very dedicated service to our community. They have enabled the research of literally thousands of students and postdocs over many years that have gone through our lab. And I am certain that they will continue their loyal and dedicated service to the community from their new home in MIT.nano. And I'm also certain that Vladimir will take very good care of them. Thank you very much.
Right outside of these doors, there is a tent. Inside, you'll find some nourishment. If you like more, Student Center is right nearby. At 1 p.m., we will reconvene and start again. Thank you.